The moving coil galvanometer consists of circular-shaped magnetic poles, which create a uniform radial magnetic field. It also consists of a current-carrying coil of many turns wounded in a rectangular shape over a soft iron core. The soft iron core increases the strength of the uniform radial magnetic field. In the radial magnetic field, the plane of the coil is always parallel to the direction of the magnetic field for any orientation. Hence, the angle between the plane of the coil and the direction of the magnetic field is always 0. And the angle between the axis of the coil and the magnetic field, theta, is always 90 degrees. A spring, denoted as SP, is connected to the axis of the soft iron core. On close observation, we find that one end of the spring is connected to the axis of the soft iron core, and the other is connected to a rigid support. A pointer is connected to the axis of the soft iron core. This pointer moves over a circular scale. Now, let us discuss the working of the moving coil galvanometer. When an electric source is connected to the terminals of the rectangular coil, a torque is produced. That is, when a current passes through the rectangular coil, two equal and opposite forces acting on either side of the coil produce a couple. In our present context, we refer to this couple as the torque. As you learnt earlier, the torque acting on the coil τ is equal to BIAN sin theta, where theta is the angle between the axis of the coil and the magnetic field. Here, theta is 90 degrees. Thus, sin 90 is 1, and we have the deflecting torque acting on the coil tau equal to BIAN, where B is the strength of the uniform magnetic field, A is the area of the current-carrying coil, N is the number of turns in the coil, and I is the current passing through the coil. Let this be equation 1. This deflecting torque in the coil develops an equal restoring torque in the spring in the direction opposite to that of the deflecting torque. Hence, these two torques are balanced. The restoring torque produced in the spring is tau is equal to k phi, where phi is the deflection shown by the pointer and k is the torsional spring constant, the torque per unit angle. Let this be equation 2. Equating the expressions 1 and 2, and on simplification, we get phi is equal to BAN by K into I. Let this be equation 3. The value of BAN by K is constant for any given galvanometer. Hence, phi is directly proportional to I. That is, if the current passing through the coil increases, the deflection of the pointer also increases. By passing a known value of current and measuring the corresponding deflection in the coil, phi is found. From this, the deflection per unit current is calculated, and then the circular scale above which the pointer moves is graduated. This is known as calibration of the galvanometer. The ratio phi to I gives the deflection per unit angle, which is defined to be the current sensitivity. From equation 3, phi is equal to BAN by K into I. Hence, the current sensitivity phi by I is equal to BAN by K. The current sensitivity of the galvanometer can be increased by increasing the number of turns in the coil. It can also be increased by increasing the area of the coil or by increasing the strength of the magnetic field.